Resume. Thank you. Yeah, I was about to do that, and then I got ahead of myself sharing the screen. And when I share the screen, there's the button to record disappears. Anyway, whatever. Here we go. Let's get this going. Okay. So, well, of what I've heard and what I've been told, this quiz is going to be focusing on elimination reactions, which is like a pretty narrow subset of reactions. I mean, they cover a lot, right? Like it's one of these broad classes, one of these 4 broad classes that you're learning right now. But well, it's kind of just one of those 4. E1 doesn't show up in as many contexts, although, well, every once in a while it can sneak up on you, but we'll get to that, right? So, I mean, I guess we'll just talk about and kind of focus on, let's see, can you see my screen? Yeah, you're able, yeah, okay, thank you. Sorry, yeah, so we'll talk about eliminations. And the key kind of idea here is that, well, I mean, we're going from like an alkyl halide, or, you know, you could have like a tosylate, etc., right? It could be whatever. And then, okay, well, you're going from that alkyl halide, and then you're forming an alkene, right? You're removing that. Okay, and this is old news, right? You've seen this before. And so we know that there are these 2 classes of them, which are, so E2, right? This is a bimolecular reaction. Yeah. Yeah, so this is bimolecular. And, well, I don't know what else is it. I mean, I guess just to give like an example of it, right? Like if you have something like this, and then you give it, generally here you want a good base and a bad nucleophile, or something that's particularly a good base, and you want it to be like a bad group for SN2, right? So you put it in I don't know, sodium hydroxide, sure, right? And then in this case, we'll wind up getting something that looks like this. And I picked a kind of nice example here because, well, whatever hydrogen we plucked off, it wouldn't matter, right? So just to show a mechanism of this, we have some hydrogens here, right? These things have to be oriented anti-periplanar, right? So we have to have this sort of situation. Okay. And, well, these electrons hop onto here, and okay, they jump over to here. Okay. And, well, this is a nice example because no matter which hydrogen we pulled off here, it wouldn't have made a difference, right? But, well, let's say that we were to give it something a bit more interesting, right? And we said similar compound, except now over here we have something that looks like this, right? And, well, there's a hydrogen over here. And so now if we give it an OH minus, well, this is a really small base, right? This is tiny, and it can fit in here. It can make its way, it can snake all along here, and it can get into there, right? And so in a case like this, you'll wind up getting a structure out along these lines, okay? And, well, this is one of the 2 possible structures because we could have pulled hydrogens off of elsewhere, right? So what is this structure called? Which one is this?
Zaitsev product?
Yeah, so this is a Zaitsev product. You could spell it however you want. There's like a million ways to spell it, right? And so the idea with the Zaitsev product is that it's more substituted. It's a more substituted double bond. That's one thing, right? And, well, what that means is that it's the more stable double bond, or more stable product. Okay. And we get this whenever we have a small base, right? One that can get in there easily. So in terms of small bases, you'll usually see OH minus. O-methyl is pretty small. O-ethyl will probably count as small. Once you start getting into like O-isopropyl, well, it's kind of sketchy. Okay, so if you do see O-isopropyl, you could probably take it as being the Zaitsev product, but well, it gets kind of iffy at that point. Right. So okay, we have the Zaitsev product, and then, well, what's the other product that we can get?
The Hoffman.
Yeah. So we could also get the Hoffman product, which looks like, and in general for the Hoffman product, you'll see O-tert butyl. This is like the most common one that you'll see being used for it, right? And it's going to pull off whatever is most easily accessible. So in a case like this, well, you'll get a structure like this. So this is Hoffman. So this is the least, well, I guess I'll just say least instead of less. So this is the least substituted. And this is when you have a really bulky base. Okay. And so I already said, well, this is a very bulky base. And maybe there's another that you'll see, which, well, it's come up before, but not very often, but it's certainly worth me telling you anyway. So you can have this structure, which is another bulky base. Okay. Anybody know the name of this by chance?
Diisopropyl amine.
Yeah, exactly. Yeah, so this is a diisopropyl amide, or
Okay.
So typically there's a lithium here. Yeah, right. So it's called lithium diisopropyl amides, or otherwise LDA. Okay. Or if you just see like this part, this is the part that's relevant, right? This is the part that we care about. So if you see something like this, well, then that's a bulky base, so you're going to do Hoffman elimination. Yeah. The reason I mentioned this base is, well, for one thing, it's shown up before for like elimination style problems, but you will also see this base, like, as I really often say, you'll see this base again in like 6 months or so. And well, at that point, you'll look back and you'll say like, oh, shoot, well, I could have used this for elimination like 6 months ago, right? And then it's not going to have made a difference. So it's worth me telling you that now anyway. Okay.
What's the last small base example that you gave?
Oh, yeah. So I mentioned isopropanol, which sometimes I've seen it used as a small base before, but it's kind of iffy.
And then what's the one before it? The O.
Oh, sorry, O-ethanol.
Oh,
So it's ethoxide, or I guess I could just draw it out. Actually, it's this.
thank you.
Yeah, I'm gonna get rid of this one because it's kind of iffy. So I don't want to. Yeah.
Just a quick question. If we have a small base, would the Hoffman product still, would there be maybe a minor Hoffman product as a result, or would it usually be just the Zaitsev product?
Yeah, so there will probably also be a minor Hoffman product. But in a case like that, especially since when you're making the, if you're making the Zaitsev product, you can kind of pull a bit off of everywhere, but don't, generally, I think you'll just have to write down the major one, or if there are equally favorable ones, like the major multiple products. Yeah. You usually won't have to write both Zaitsev and Hoffman.
For E2, do we have to write any solvent?
Because sometimes I like see nothing written, but I don't really know.
Yeah, so with E2, solvent is a little bit is not as like clearly defined as it is with SN2 and SN1. Actually, when you're doing E2, solvent can kind of clue you into what you're doing. So because, for example, with a case like this, right, you can't dissolve sodium hydroxide, this guy, in like a polar aprotic solvent. Like it won't dissolve very much at all. So in fact, usually you'll probably have to put it in some kind of you'll have to put it in some kind of protic solvent. So for example, here you might use methanol, right? And if you see something like this and it's like methanol here, that might tell you like, oh, this solvent's really bad for SN2. So this might be an E2 reaction instead. Or for example, this might be water. Although I don't know if you'll see that one very often. Yeah. So for example, this could be like methanol. And this one here, if you're using tert-butanol, then it's probably going to be tert-butanol as the solvent. So oftentimes, for example, in a case like this, you might see this written as, yeah, so you'll see this thing up here, these conditions written as KOT butoxide / HOT butoxide. You might see it written this way. Yeah, on the exams and quizzes that they give, I think they usually tend to write them as they tend to draw out the structure, but they might write this, put this down.
Can you explain this solvent? Like, why would this be a good solvent for this one?
Yeah, it's because it's still because if you want to have this thing floating around, you need it to be a protic solvent, because you need if you want to have a minus charge around, you need the solvent to be able to like support that, in a way to say. Yeah, so a non-protic or aprotic solvent wouldn't be as good about this, about being able to have this around. Yeah. Yeah, I should say like solvent is a little bit less defined. Like it's there's kind of a reason that they didn't tell you very much about solvent for E2, because well, it's not as like clear as with SN2. You need like a polar aprotic solvent, right? Like you're not really going to be able to do SN2 very well without that. But in a case like this, it's not as clear. But so yeah, you might see things that are normally not SN2 solvents, and that might help clue you in that it's E2. Yeah. Yeah. Okay. Anyway, someone asked in the chat like a while ago, and I've seen it. I just haven't gotten to it because I was going through this. If we could look at like an energy diagram for an E2, right? And then, well, I mean, this is the reaction coordinate, right? And this we can call energy, sure. And then, well, the thing with E2 is that this is how we've written the mechanism, right? Let's say we have, I don't know, we'll pick something really simple, right? So that we don't have to just write forever, right? So if we have, this, bromoethane, this thing, right? And then we put it in sodium hydroxide. Well, it's gonna maybe let me write it this way, right? So we start off with this is just normal and fine. And then we go to a transition state, which we don't focus on so much for E2 because, well, it's not that interesting. But what we do is, well, the bond to the bromine kind of starts breaking. The double bond here kind of starts forming. The bond to the hydrogen starts breaking. And the bond to the hydroxide starts forming. And I mean, yeah, this is the transition state. Let me call it TS instead of using this fancy symbol, right? And then, well, we get a double bond out, right? And that's like, you know, this transition state is, it's kind of just saying, okay, well, the electrons are moving. Like that's kind of it. Right. And so all that we know is that, well, we have a transition state up here, and then we've got like a starting state and an ending state. Well, I mean, okay. And then we just fill in the lines. Exactly which of these is higher or lower, which of the start and the end is higher and or lower will depend on what reaction you're doing. Yeah, so it's yeah, I don't think you could say in general which of the two will be higher or lower. Yeah, I don't think you can. But if anybody has any insight on that.
Adam, this is just like what I'm thinking about the energy diagram in terms of like, I guess, knowing what result you get for the product. So like, I would imagine that maybe for the Hoffman product, because you are abstracting the hydrogen that's easier to access, like maybe like the energy graph would show a more kinetically nice reaction, whereas like a final Zaitsev product, because it is more stable, might also have that reflected in some way. I don't know. Like, I don't know how to quantify that, but
yeah, I don't know. That's a good point. Whenever I've seen stuff about Hoffman or Zaitsev products, it's always just been in terms of like kinetically favorable, right? Because it's like it's kind of a steric effect. Like the terbutyl group is just so big and it gets in the way. I haven't seen it reflected in an energy diagram before. Yeah, maybe it can be. I don't know. I'm trying to think about it. This might be a good section to check in the book, and I haven't looked at the book or I haven't at least looked for this specifically. I don't know if they talk about it, and I'll guess that they probably don't, but they might. Yeah, I don't know. I haven't seen it before, so.
yeah, I haven't either, like anything, I guess, that in depth as like so far as to really reflect that graphically. But I guess I was just thinking in terms of like, maybe if you did run an experiment and like, you know, plot the data, you could see some sort of difference. I don't know.
Maybe. Yeah,
Sorry about that tangent.
Sure. Yeah, I don't know. I'm not sure. It would be a weird question for sure. Yeah, I think like.
Well, they love adding energy diagrams, so that's why I was asking the question, just to sort of caution myself as to what could come up, because that's been sort of a recurring theme, just a surprise energy diagram. But yeah. So that's that.
They've been giving a lot of surprise questions this year, so that doesn't surprise me. Yeah. Yeah, I think it does depend on the compound, but maybe not. So I wrote E here, and if I guess like, and now I'm talking like outside of the course, right? But like really this should be like a Gibbs free energy or something. And that means it really depends on like the reaction conditions and what's favorable. And if you want a reaction to happen, then the Gibbs free energy has to go down. And so in that case, then, well, then you know that it looks like this, right? And yeah, but I guess this is probably not really what they're looking for, because, well, Gibbs free energy, you can make the diagram look differently if you want to, and that's more complicated. Yeah. yeah, I don't know. I haven't seen something like that come up before, which is kind of weird. It's something that's good to look up, and if we have time at the end, I'll try to remember or remind me, and we could look it up and try to think about it. I do so. I mean, part of the thing is that like that energy diagram was a little bit like not super interesting because it just had, well, start here, there's a bump, and then it goes down, as opposed to, you know, a full proper like multiple transition state or intermediate states or anything. So I have the feeling and like from kind of experience, once you get to this part of the course where there are reactions, I mean, it's really about reactions. And they'll try to ask like, probably there are like, there are like 3 classes of questions. So there's predict the products or provide the reagents, one of those, right? And those are just like the short answer ones that, I mean, there were like 20 of them on the last quiz, so you got to see them. Then there's mechanism product problems, which will usually give you the start, the reagent, and the product, and you have to provide like how each of those steps go. And then, well, there's also synthesis problems, which, well, surprised many of you last quiz. Yeah, they're where they give you a start and a finish, and they tell you to say what happens or what you do in the middle to get from point A to point B. Yeah. And I have the feeling that they'll focus on those. Those are the kind of like most common and good ones. Additional types of questions that they might ask, I mean, they very well could ask, for example, like ranking questions. They could ask you to say which of these are, you know, rank these nucleophiles and rank these bases. Or, for example, which of these compounds will undergo SN2 easiest, and then you're asked to order them somehow. Those are the sorts of things that I could see them giving. Ranking problems can show up in this. They've shown up in this style of problem or at this point in the course before. So if you thought you were done with ranking problems when it came to acids and bases, well, they're still around. So that's the other type of problem that I could see them giving. But they might pull anything out. So yeah. Okay. How about we keep going? Where am I on time? All right, I've talked a little bit, but not overwhelmingly. And then we'll get to problems, right? So, okay, this is E2, right? And E2, okay, we're cool, good. We've talked about it. And, well, after E2, there's also E1, and there's not as much to say about E1. It's, I don't know, it's in practice, or as far as you'll see it for most times ever, the way that E1 looks is just that you have an alcohol and then you give it concentrated sulfuric acid, right? And then, okay, well, it pulls this off. And, well, maybe the most important thing that I could say about this, and this is something that I really have, well, I could totally see them trying to trick you with. Something that's really important is the fact that this is reversible, okay? So not only do you learn E1, but you're also getting twice the bang for your buck or whatever. And you also get a reaction, you also get a reverse reaction, right? So for example, you could have a compound that looks like this, right? I don't know, I just picked one. Okay. And they could say, all right, well, now it's not concentrated, but they could say, okay, well, it's dilute sulfuric acid, right? They could say that for like no reason they can't. And then, well, I mean, what you could find is that, well, you can get an alcohol out. And in fact, you can get another one. Okay.
Would you need a double bond in the to break?
Yeah.
If you're gonna do the reverse E2, E1.
Mm-hmm. Yeah. So it would have to start from an alkene, and then you're going to an alcohol.
So would it be the sulfuric acid just like donates a hydrogen, or how does that exactly work, sort of mechanistically?
Yeah. So
Could you draw the arrow?
yeah, exactly. So this is and and I don't mean to like throw a lot of terminology at you at once, because I know that like you're thinking about, well, you're thinking about how to solve problems, which is what you should be thinking about. But we can kind of lean on the principle of microscopic reversibility here, which if you don't remember what that term means, that's totally fine. In fact, I think it was the very first question on the final that I took when I took the class, and I stared at it and I was like, I literally have never, like, I know I've heard of this term once, and yeah. So anyway, so the principle of microscopic reversibility just says the mechanism that a reaction takes in the forward direction, it takes the same in the reverse direction, right? So I just remember one of the two of these directions, because there's no reason to remember both, because I could just flip it around backwards. So for example, I know that this is the product. So what I can do is I could just lean on the E1 mechanism, okay? So here we go. This is what we know we can have, right? And then if we have H2SO4, well, okay, one of these electrons is going to pull a hydrogen off of here, which is to say this gets protonated, plus, right? And then, okay, well, this thing will just come off. Right? And then, okay, there's a hydrogen over here. And now we have this HSO4 minus, right? This counter ion. You could also use water here. They're not going to fault you if you use water. So why don't I even just do that? So here we go. Here's water. And, well, it's going to push these electrons onto here. Okay. And that is it. That is the arrow pushing mechanism, right? And so now if we were going backwards, well, we would just flip these arrows around. So if we were going like this, well, I'm going to donate these electrons to a water, right? And then there's that carbocation, right? And now I've got a bunch of other water that's floating around, which is going to come down here. The water will attach, right? But it's a carbocation. Okay. And then you could take it from there. Okay. So this is right. It's not often that we get to say that we really invoke the principle of microscopic reversibility, but this is one chance where we do. So the mechanism is the same going forwards as it is going backwards. And so we can just flip them around. Okay. And this is what that looks like. Right. And well, this is just an example that I don't know, I just pulled off the top of my head. But the main point is that they could ask you to do this. This is an alkene reaction. You're going to learn about alkene reactions over the next few weeks, right? That's what the next few weeks are going to be about. And this one will show up again. You'll see this, and they'll say, I don't know, in lecture or something, they'll just say like, yeah, this is the reverse of E1. You've already learned this, right? Well, yeah, you've seen this before. So you already have one reaction kind of under your belt that now that the course is getting into just a lot of reactions, like lists and lists of reactions and a whole ton of them, well, you already got one, I guess. So kind of useful. Yeah. Okay.
So on the quiz, are we going to be tested equally on E1 and E2, or like from your understanding, is it going to be mainly E2 with some E1 reactions?
Oh, I don't know. It's really hard for me to tell. my impression was that they're planning on kind of synthesizing all of these things that you've learned, right? So having it kind of be about combining SN1, SN2, E1, E2. Although it's hard for me to exactly say. I don't know. I'm not involved with I haven't seen or I'm not involved with writing or making the quiz. So it's hard for me to tell. Okay.
Just to quickly confirm, so E1 is reversible, E2 is irreversible, right?
Yeah, that sounds right.
And then SN1 and SN2, would SN1 also be reversible and SN2 be irreversible?
Yeah, exactly. Yeah. When we're talking about E1, there's an extra important thing. So with E1, there's also kind of the important fact, which is that we can have rearrangements, right? So we have carbocations, and whenever you have carbocations, always, whenever, you need to look out for rearrangements. Okay. And this is the reason I bring this up. Rearrangements are irreversible. Okay. So E1 in general, yeah, E1 is reversible, right? We use concentrated sulfuric acid, so that way we get, most of the product out that we want and all that, and that's nice and all, but if there's a rearrangement, you're not going to go backwards. You're not going to change. And I mean, that's kind of like purely in nature of the fact that when you do a rearrangement, you go from something that's pretty unstable, something that's really like high energy and hard to get, and you're going to something that's much lower energy, much like more stable. It takes a lot of work to do it, but once you're there, it's like so much better that you're not going to go backwards. You're not going to redo that. So, yeah, the fact that you have these carbocations means you can get rearrangements. Those rearrangement steps are irreversible. So, for example, you could very well see yourself writing like, okay, we start with A, and then we go to B, right? And then we go to C, and then, okay, we rearrange. Right? And then we go to D, and then, okay, well, you could go back to drawing equilibrium arrows if you want, right? But when this happens, it's a forward arrow, straight through. Yeah. Okay. Yeah. In practice, like I kind of mentioned, this is, if you have an alcohol, you give it concentrated sulfuric acid, and that's kind of what it does. There are minor variations on it. So for example, well, we'll see some in like the problems, but yeah, so there you could vary it, right? It doesn't have to be an alcohol, and it doesn't have to be that. So I mean, you could do something else, like for example, right? I don't know. I don't know if I should give an example, this because this one I'm just coming up with on the spot, but well, no, okay, let's not do this one. Sorry, I don't mean to erase, but how about I just give you an actual practice problem that I had planned to give later anyway. So here's a ring, okay? Here's a chlorine. Sorry. Okay. Here's a chlorine, right? And well, let's say we have CpH3, okay? Where, so this pH is, it's a phenyl ring. It's one of these, right? Or alternatively, it's this. Okay. So this CpH3 is huge. It's massive, right? You know how tert-butyl can't, like, if you have like a ring with like tert-butyl, right? If you have one of these, right? This thing can't ring flip. Okay, well, this one's like not being able to ring flip on steroids. So this one's certainly not going to flip and do anything, right? But the question is, well, what reagents or what conditions do I have to give it in order to get to the eliminated product. Okay. And well, I'm talking about it in the E1 section, so that should give you a bit of a hint. But well, anybody want to give it a shot?
I guess to get that specific product, could you like give it silver nitrate and precipitate off the chlorine and then do E1?
Ah, okay. So yeah, you could actually yeah, that is a great thought. Yeah, so you could give it, let's say,
Only because it's E1.
yeah, so you,
Because I don't know
I
if
think,
that's the most efficient way.
yeah, so okay, well, here's one way. Okay, so you could give it silver nitrate. Okay. Is this going to do it, though? There's something else that you definitely need to do this.
You need a base to abstract a hydrogen so that its electrons can make a double bond. Like for E1.
Yeah, okay. Well, we're kind of getting that for free, right? Because we have this nitrate. So that'll be the counter ion. That'll be what'll pull off the hydrogen. Think of something else.
Heat.
Yeah, exactly. Yeah, you gotta blast the shit out of this. Okay. Yes. So that is you will definitely need heat to do this reaction. What I'll actually also say is you don't need silver nitrate. So one other option, anything else you can give it? It's not a special, nothing special. Any other thoughts?
Would you do the typical H2SO4? Or not with chlorine?
I'm thinking even simpler than that.
Could you use just a bulky base like T-butyl for to ensure into E2?
You don't need a base very much either.
Proton?
No, so huh?
A proton? Or because
Yeah,
that-
well, yeah, I was just gonna say you could just give it a solvent, right?
Okay.
So you could very well put it in a solvent. Methanol is a good one, right? Perfectly fine. Just throw this in methanol and heat it to hell. And well, this reaction will happen. So either of these two is probably perfectly fine. This is the one that I was thinking of, and which I got from the place I pulled this problem from. But this would probably also work pretty nicely. Yeah, the silver chloride thing is also probably pretty nice.
Then how do you know that, like from looking at this would be E1? Because normally I thought it was like an alcohol with a concentrated acid as like the indicators for it.
Yeah. So yeah, it's typically that, but well, every once in a while there.
Is it because the methyl group? Sorry, I'll turn my camera. The methyl group next to the chlorine on the other carbon is in axial position, and so there's no, in order to form the double bond between the two methyl groups, it can't be E2. Is that a reasonable explanation?
Oh yeah, that is a good explanation. In fact, yeah, yeah. I think you said this one was axial. So this hydrogen's equatorial, right?
Yeah.
Yeah, right. And then, although I might have misheard anyway, but yeah. So that is true, right? You do know this will have to be through E1 because, well, I guess for one thing, this ring definitely can't flip, but it also doesn't help that the hydrogen that's adjacent, which is in this position where we want the double bond to be at the end, well, it's yeah. So this hydrogen isn't going to be able to really even go in the favorable position anyway.
I actually had a quick follow-up question from that thought. If you draw like out all the hydrogens in the chair conformation that you drew, there, like, I don't know if this is right, but there is one axial hydrogen available. So like, is it because we're limited to the product that they gave us, and like that's kind of what we're basing our two possibilities off of also?
Yeah. Yeah. So
Okay.
so in this case, we are given that this is what we want.
Mhm.
So in that case, we're gonna have to do an E1, given this structure. So, well, given that this quiz is primarily focusing on elimination, apparently, this is a good sort of thing to keep your mind on, keep your eye on, right? If you see a thing where there's like an alkyl halide, and they say, okay, well, I'm giving it any old solvent and a lot of heat, that might be E1. Or if they're saying, for example, this silver nitrate and heat, that might be another another good option is E1. Let's do E1. Yeah.
Sorry, one question. If you weren't given the product, would you still assume that it went there, or would you assume it went with the axial hydrogen?
Oh, well, then we'd have no idea because I didn't give you the reaction conditions. It would depend on what that was. Yeah. Yeah. Okay.
I'm sorry if you said this already, but could you use concentrated sulfuric acid and heat for this, or would that not work?
No, it wouldn't. That will only work for alcohols.
Okay,
Yeah.
thank you.
Yeah, because the way that the sulfuric acid works is by protonating the alcohol, which forms water. And hey, water is a pretty nice leaving group, right? Because it's just water. So in that case, it'll come off. In this case, you can't protonate that chlorine. Like, I don't know. Maybe you can. It doesn't make a lot of sense to. So yeah, in this case, you got to go through this way. Okay.
If we weren't given like the product and we had like the MEOH, would it still be possible for us to get SN1 products?
Yes, I think it would be.
So in that case, the correct answer would be both the E1 and SN1 products. And would one of them be favored in this case?
Oh, I don't know. It's hard to say if either would really be favored. I think if you're heating it so much, that might kind of favor towards E1, but I think SN1 also kind of tends to use heat, so it's hard to exactly say which one would be more favorable. Yeah. Okay. Cool. Shall we get to problems? All right. So we will start with the problems for this week. Just because, well, they're kind of more geared towards elimination and that sort of thing. And then we'll go back towards what we had last week. And from there, if we still have time, I'll start doing the problems that I kind of prepared. All right, let's see. And okay, here we go. All right. Why don't we get started with this? Okay. So here we go. First thing. Okay. Well, we're given this initial reactant, and we're given the this stuff, right? Reagents. That's what they're called, and the conditions, right? Okay. And then we're asked to say, okay, well, which of these is viable or are viable products can we actually get, and then what type of reaction is it? So, okay. Here we go. We have this structure, and then we're putting in a whole ton of methanol and in a lot of heat. So what type of reactions are those going to be? First off, of these four, SN1, SN2, E1, E2, what are we doing here?
E2.
SN1.
Okay, so I heard SN1 and E something. What was the E?
E2.
Ah, okay. So what makes you say E2?
Because elimination reactions are favored by heat, and actually, based on the previous example, maybe E1 would be a better choice.
Yeah, I'd agree with you. E1 will work out well here. And more than just based on the previous example, the reason E1 will work out pretty well, or rather, the reason you won't get very much E2 is because this is just methanol. This is not like a particularly good base. And when we're doing E2, we usually want really good bases. So not going to work in this case, but instead we will get some E1, again, because we're just putting it in a lot of heat with not a lot else to react with. So, okay, which of these are SN1 or E1 products?
Wait, sorry, could you repeat what you said? Is it SN1 or E1 or both?
It's both.
The first three are the correct results. The first one is the E1, and then the second two are SN1 products.
Yeah, exactly. Okay, so, well, it's all three of these. Yeah, here we go.
Why couldn't you get the other products if there's like excess? Couldn't these products react again?
So the difference is on these products, we have this here, right?
Yeah, but what I'm thinking is then you'd have two SN1 reactions. So you'd like react for these first products and then you could react again since there's excess.
Yeah.
We can't do elimination on sp2 hybridized things, right?
That's the biggest idea. Yeah. Yeah, that's right. So even more than that, these are these aromatic rings, which is what we call them, which is these 6 carbon rings with 3 double bonds. And at this part of the course, you can't touch these. Like, leave these alone. Okay. There will be a point where you're allowed to do stuff with them, but these things are super stable and super unreactive. And so even if there's an iodine, which is like, really nice, and it's just like begging to get replaced, you can't do it. Yeah, getting rid of something on one of these rings is a lot harder, and it takes some more special tools that well, you'll see them next semester. But for now, whenever something is attached to an aromatic ring, like the exact bond that's attached to it, like it's gotta stay as is. Yeah. Okay. Oh, let me say, let me keep that. Yeah. So you'll want to leave these alone. Okay, cool. Well, that's good. How about we do another? Okay. Well, we move this down. Okay. Whatever. All right, cool. So we have this structure over here, which is, well, it's drawn in a little bit of a complicated way, and it's also got a fluorine, which we don't see that often, and it's like that. And then, okay, there's a wedge, right? Because this is a chiral center here, because this side has a fluorine, right? And then we're saying we're giving it iodine. Okay. Iodide anions. You might see this on like a quiz, for example, as potassium iodide, right? The main idea being just this part, which is the I minus. Okay. And then we put it in the solvent. Somebody want to tell everyone what the solvent is? Anyone remember? No. Okay. Well, maybe more relevant is, well, okay. Let me just tell you then. Well, it's a protic solvent, right? No, wait, sorry. It is a polar solvent, is what I meant to say. Sorry if I confused you. It is a polar solvent because, well, it has this this carbonyl. Okay. Is it a protic or aprotic solvent?
Protic?
So what makes you say protic?
There's a hydrogen.
Can we take the hydrogen off?
Maybe not.
Yeah, you're right. So we can't. It's on an aldehyde, and well, generally we're not able to break carbon-hydrogen bonds. So that hydrogen's there to stay. And none of the other hydrogens on here are nice and like easy to take off. So this is a polar aprotic solvent. Okay, which is nice for SN1 or SN2?
2.
Yeah, that's right. Okay. Yeah, so that's right. Okay. And I should, give you the answer here. So this is a common SN2 solvent. It's called dimethylformamide, or DMF. So you might see either of these two show up, but in a case like that where, nobody remember what it is, which is reasonable because it's not often that you see the structure of a thing like this. Going through a process like that is helpful, which is saying, does it have protons that can easily come off? And is it polar? Generally, all of the solvents that we're going to work with are polar.
Wait, sorry, could you repeat why its hydrogen couldn't come off?
Yeah. I mean, this is the only hydrogen that stands out, but we can't pull hydrogens off of aldehydes. Like this sort of thing. This doesn't happen. I don't remember what the pKa of one of these things is, or like how easily it'll come off. But a hydrogen like this won't come off generally. And I think for like a long time, you're not going to see any examples where hydrogens can come off of carbons. I mean, yes, you could do E1 and SN. You could do E1 and E2, where something is pulling the hydrogens off, but just like, deciding that they want to come off, is not gonna. You can't do that. Well, yeah.
Okay, thank you.
Yeah. And at the risk of confusing you, this is again and over again, what I just said. It's an exception that can be broken, and it will be in a long time from now. But for now, and this in particular, doesn't happen. This hydrogen that's over here, whoops, this hydrogen that's over here doesn't go anywhere. So yeah, that's why this is aprotic. Yeah. Okay. So this is polar aprotic. The easy way to remember. So a protic solvent. So a protic solvent has to have either an OH or an NH. So if it doesn't have either of those, then it's aprotic. That's the only two. This is it. Yeah. Maybe if somebody's really picky, they can say, oh, well, it can have SH too, or something like that. But I've never seen something like that, and it's kind of unlikely that it would show up. So yeah, it's got to have one of those. Okay. Well, here we are. So we've got this, and we've got an iodine here, and it's in an SN2 solvent. So what are we going to do?
Backside attack for SN2.
Right. We have two places where we can do that. Where are we going to do it?
The bromine.
Yeah. Okay.
Or like
So
not
we're
actually the bromine, but when it leaves. Like
oh
the
yeah,
carbon.
I know what you mean. Right. So yeah, the iodine is going to come around here and is going to go after the carbon, right? And then that bromine is going to pop off. Okay. And then we get this structure, and what happens here? Whoops, not bromine, but what happens?
The stereochemistry flips.
Yeah, exactly. Right. So we get flipped stereochemistry. Okay. Is that somewhere in this list? Well, yeah, it is. That's here. Okay. And I should have circled SN2 because we said that a while ago. Okay. Can we get compound number 2? No, I'm seeing nons. No. Why not?
Because the stereochem doesn't flip there.
Yeah, exactly. Yeah. That's right. The stereochemistry doesn't flip. This is not going to go through SN1 because the solvent's not good for it, and also secondary carbocations aren't very good. We don't want those. So 2 is bad, right? So 2 has wrong stereochem for SN2. Okay. What's wrong with 1? Is there anything wrong with 1?
Yeah, they have the wrong leaving group.
Yeah. Yeah, fluorine is a terrible leaving group. Yeah, so we can't take the fluorine off. Yeah, carbon-fluorine bonds are basically untouchable. Like they truly are. For example, Teflon on like your pans and cookware is just a long chain of carbons and fluorines attached to it because it's so inert and doesn't do anything. Anyway, that's a fun fact, but yeah. Can we get 4 or 5? Are those reasonable? No? Any thoughts why?
I just know Ravelli gave us a sheet, and when you only have a good nucleophile, you'll only get SN2.
Yeah, so I is a really good
It's too weak
nucleophile.
of a base.
Yeah, yeah, exactly. Right. I is a terrible base. It's like the worst base imaginable. Not really, but it's really, really bad as a base. I is a terrible base. Yeah, it's not good. Okay. So, well, that crosses these out. Cool. Okay. I need to save these things. Here we go. Okay. Cool. Let's keep going. All right, next one. The last of these, like, lots of product ones. Here we go. Oops. Sorry. Sorry if this whole program thing is disorienting. I swear one day I'm going to get good at Photoshop. And I say that every time, but one of these days I'm actually going to figure it out. So here we go. All right. Okay, we've got this structure over here. So it's a tertiary bromide, right? Always good to ask yourself, what type of thing is it? Where's the thing substituted, right? And well, we've got this methoxide. And what really stands out to you about methoxide?
It's a strong base, but could also be a strong nucleophile based on, like, I guess the other conditions.
Yeah. So well, for one thing, it's a really good base. Yeah. So this guy is a really good base. Right? It's also a really good nucleophile. Well, not really, but it's pretty good. Right? There are better ones, no question, but well, this one works fairly well. Okay. So this tells us that we could do E2, right? Because we want really good bases for E2. And this tells us that we could do SN2. Can we do SN2?
No, because tertiary.
Yeah, exactly. Yeah, so this is tertiary. So we can't do that. All right. So instead, what do we get? We get E2, right? Okay, so let's circle E2. We know we're going to get that. Okay. Which of these are E2 products?
Two and four.
Yeah,
But-
2 and 4. And?
It's a small base, so it would just be the ZZ product, which is two.
Exactly. Yeah, you're right. So this is the product that we're forming. This is major, right? And you can kind of say, all right, well, this one will be minor, but we're just going to focus on the ZZ product. Right? This is the Hoffman product. Okay. So that's what we will, well, so we know that. Okay. And then maybe you might ask, well, can't you kind of get SN1 happen some of the time too? And yeah, technically you could, but E2 will definitely dominate in this case because we have a really good base. So it's not as likely to have, SN1 is not as likely to happen in this case. Okay. All right.
Wait, why would you have a SN1 ever in this case?
I mean, no, for all intents and purposes, no. Yeah, if you were given a problem like this and you put SN1, they would mark it wrong. So I'll just say no. Yeah, just because E2 will happen so much faster and so much more favorably that it's not going to be SN1. Okay. Okay, let's keep moving to the next problems. Since well, yeah, let's keep going. Oops, pressing the wrong button. Okay. All right, so here we go. We have predict the products or various assorted variations on them. Here we go. All right. Okay. We're given this structure over here, and it's given sodium hydroxide. In fact, I already used this example before, so anybody want to remind me what happens?
The E2 reaction occurs, forming a double bond.
Yeah, right. And all of these hydrogens, they're pretty much the same. So it doesn't matter which one we pull off, and we get this structure out at the end. Okay. To draw what that actually looks like, what happens. Right. So here's an OH. Okay. We're going to take off this hydrogen. The electrons are going to move down to this bond. The bromine is going to pop off. And that's it. One step. Nice and clean. Okay. Next up, we want to get only this isomer of this compound. And I should say, this is a very common type of problem that you'll see. In fact, you will almost certainly, almost unquestionably see one of these problems on the test. Either give the reactant, the thing that you start with, or something where it's like give the product given this really complicated reactant. So we need to figure out how we get to this. Any thoughts?
Well, we see that it's a base and that's generally pretty bulky. So this is probably the Hoffman product of an E2 reaction.
You're right. Great. Okay, so we know this is going to be the Hoffman product. Okay. So if I was to draw this whole structure back out, okay. Well, yeah, okay. So we're taking the less substituted thing. The question is, of these two carbons, here and here, well, where are we putting our bromine? Which one of these two is it going to be?
Probably the left one.
Wouldn't it be the right because it's more substituted? So that would be the Zaitsev. If like the other thing it can create would be the Zaitsev.
Yeah, so if we were creating the Zaitsev product, if we were creating the Zaitsev product, what would actually happen if it was over here? If we were going Zaitsev, then it would take off this hydrogen over here. And so we would get a double bond over here because this is the most substituted, but this is besides the point. Yeah, in this case, we know that we're just forming the Hoffman product. Yeah. So any thoughts for left or right?
Wouldn't it be left so there's not like two equivalent hydrogens that could be subtracted, so you'd get a mix of products? Like if you put it on the right. Because you can rotate this single bond, so then you could be like eliminating two hydrogens if you had it on the right instead of just one.
I see what you mean. Yeah, this is yeah, you could put it on the left.
If you put on the left though, wouldn't that not be the Hoffman product? Like
oh yeah. Yes. Yeah, thank you. Yeah, so if you did put it on the left, which is a good point, if you put it on the left and now you gave it O-tert butyl, it'll come around and take this one off. Right? And maybe we should have just started with this and said, okay, well, suppose it's on the left, what happens? right? So this is the wrong product. Okay. And so that means the bromine is on the right. Okay. So there's the bromine. Okay, there's the rest of the structure. And, well, what do we know about the hydrogen that is opposite to the bromine?
It's anti-periplanar.
Exactly, yeah. Okay. So this hydrogen has to be anti-periplanar. In this case, it doesn't matter, right? Because we have another hydrogen here. So on this side over here, it's not a chiral center. Right.
But I kind of, going back to what Andrea said, with the bromine on that, on that carbon, you can get two different stereoisomers because the hydrogens can rotate. So you could get it such that the methyl is on the same side as double bond as the, is that a phenyl? No, not a phenyl. As the cyclopentane.
Yeah, you're actually
Yeah, I
right.
just got my information from another like problem. I think it might have been in the book. I'm not entirely sure.
So even though like the Hoffman product may be more dominant, the only way you can get only this stereoisomer, I think, is if the bromine's on the left carbon.
Yeah, although that doesn't really work with the
And maybe it's like
with the reactant. Yeah, let me check what they're looking for in this problem, because I see what you're saying. Yeah. Okay. Yeah, how about we, okay. Yeah, maybe this part is bad. Let's do sodium. Let's do hydroxide instead. Yeah.
Just a quick question.
Yep.
If in this situation, the bromine can interact with the anti-periplanar hydrogen and also the syn. I think the syn was the other one. Would it not mean that it would choose the anti configuration just because it's more preferable?
You should almost always choose the anti.
Well, yeah, but as in that it only then would form that particular stereoisomer, because it would not be preferable for it to flip that, for it to spin, I guess. I don't know whether I'm making sense here, but
Yeah. I mean, in this case, we're able to move either of these hydrogens to be anti-periplanar. So that's what in this case gets us two stereoisomers. And then in this case, well, given that we're changing it to be an OH, right? Yeah. Well, in this case, this is nice because we're getting just one of the two. If this is the case, then we're going to have to impose the stereochemistry here. We're going to have to say what it is, right? So we're going to have to put this hydrogen down here, right? And that fixes what the stereocenter is, what it looks like. Yeah. Yeah, this is a nicer way to do it. Right. Let's get rid of all that. Cool. Yeah. Okay. And so now if we do this, well, now we're going to get the Zaitsev product like God intended. And then now we only get one. Okay. One thing. And yes, and earlier I was saying like, oh, you're going to definitely see one of these problems. And so maybe it's just worth it to look at another. And I'm just going to think of one on the spot because I love doing this to myself. Yeah. So let's say we're given something like this, right? And then given a wedge for, I don't know, a phenyl group. is something that they like to give you. Given a dash for a, I don't know what they want to give you, like a terp butyl group, screw it. And then there's a hydrogen down here, and then they give you a wedge up here, right? And then I don't know what's somebody's favorite group or favorite thing to attach to a molecule. Anyone? I literally don't know. Let's just give it a methyl
group.
Yeah, let's give it an ethyl group. That's your favorite thing to attach to molecules?
Who's not there yet?
Yeah, I know.
A large variety.
Yeah. So this is good. This works, right? We have this bromine, we have this hydrogen, and like I could very much see there being, as in the past, there's consistently been a problem like this where they ask, okay, well, you're given this structure, and then, you know, put it in some base, whatever, right? And then what's the product, right? And so the idea is just to keep track of the stereochemistry. So what you always want to do in this case, like always, is if it's not already anti-periplanar, make it anti-periplanar and do it carefully. If you have like one of those molecular modeling kits, this problem might be a time to just use it, right? So whatever way they give you the molecule, if you're using a modeling kit, for example, assemble it that way, and then just rotate it and see what you get so that it's anti-periplanar. And then copy it back down on your page and resume the problem at that point, right? But once we're here, okay, the mechanism's not complicated again, right? And the idea here is that we take this whole molecule and we flatten it. At least this is the way that I like to think about it. So we just take this whole thing and we just squish it down into one plane, right? So I have it drawn like a, like I don't know, like this, right? It's like a whole big thing in space, right? But there are two things coming towards you, and two things coming away from you, right? And you just want to squish those so that it looks the same when you make a double bond. I don't know how much better I could explain it than that, but we want to we know that this phenyl over here was coming towards us. So there we go, it's towards us. You know that this methyl on this side was coming towards us, right? And then, well, we have the opposite two sides. And this is what we wanted. This is like a really common thing that they like to ask. So I would expect one. Or I'm just totally overhyping this and they're not going to ask a thing about it, but whatever. Every once in a while that happens and I get real pissed off, or I get annoyed because they do me like that. Or really they do, I mean, they do you guys like that, but anyway. Cool. All right, we've used up a whole bunch of room. Someone was going to ask a question or no?
Yeah, I have a quick question about your answer.
Yeah.
How do you know the final arrangement? Like, are you saying we want it to be an E isomer, so you're putting the higher ranking groups across from each other?
No, so I haven't said whether I want it to be E or Z or cis or trans or any of that. This is what we're given. So we're given this thing up here, and they just say do E2 on it. And because both of these are chiral centers, that sets in stone what the final product is going to look like. Because the only way we do E2 is when it's in, sorry, not when it's in, when it's anti-periplanar, right? So like the fact that the molecule looks like this, right? And then, you know, we can draw on the rest. Oops. anyway, the whole point is the fact that the molecule looks like this, it sets what the final stereochemistry is. So we don't get a say in it. We just have to find what it is. The reason being it has to be anti-periplanar like this. So we take these and we move them down to here, and we take these and we move them up because the whole molecule gets squished and flattened.
Got it. Thank you.
Yeah. Yeah, hopefully that kind of explains and covers it best. Yeah, it comes from the fact that you can only do this when it's anti-periplanar. Is this the shortest way I could say it? But yeah. Okay. Cool. And so keeping up with this, all right, up here, C. What happens? What kind of reaction is C?
SN2.
Yeah, there we go. Yeah, it's SN2. Okay. Oh, let me draw this thing for the. All right. Anyway, this is SN2, right? Anything special going on here? No, not really. It's just normal SN2, and like you've said before, invert stereochemistry. That's it, right? This is SN2 on a secondary carbon, which is already pretty dicey, right? The fact that we have this thing, this S-methyl, I don't even know what it's really called, but whatever, it doesn't matter. That's a really, really good nucleophile. It's like one of the best ones that we have access to, or that we see in this class. So the fact that it's secondary, we can kind of overlook that, right? We can look the other way, you might say. Yeah. Okay, over here, look, we've got one of these problems that we've mentioned before, right? We have this problem with a deuterium, and then we've got a hydrogen, right? And deuterium, this D it reacts the same as any other hydrogen. It's just labeled so we can keep track of it. So we've got to be a little bit careful about what we do here, right? So here we go. This is an O-tert butyl here, and we have this bromine. So what type of reaction does it look like we're going to do?
E2.
Yeah, E2, but which E2?
Anti. Like,
Well,
because the bromine and hydrogen are good to go. Like they're in position.
Yeah, okay. Well, yeah.
I don't know if that's what you're asking.
Well, that's good and important anyway. Because we're gonna pull off the hydrogen, right? As opposed to the deuterium. And we'll show why we do that in a second. But we need to justify why we're pulling something off this carbon in the first place as opposed to this one.
It's a Hoffman product.
Yeah, okay. And now the chorus sings and it's Hoffman product, right? So we're pulling off these because it's Hoffman.
But couldn't you like anyway not like subtract that hydrogen just because it's not anti-periplanar?
Right. So in this case, you have to draw out the ring structure, or, I mean, you could also just see it, which works for some people. But drawing out the ring structure is kind of important. And this is one of those times where it's important to label and mark your hydrogens. So I'm going to set this hydrogen to be there. So that's where the ethyl group goes, because that's the point up, right? And then going around this way looks like this, right? Let me draw that arrow in red so that it's clear what I mean. Yeah. Oh my God. I'm getting like a million emails that are like, can you send me the workshop worksheet? we have workshop right now. Anyway, yeah. So here we go. We have this, right? So we fill in the rest. So there's the bromine, there's the hydrogen, and there's the deuterium. And okay, lucky us, right? We drew it like this. We drew it the right way, right? But you might have also drawn it, and I should use different arrows. You might have also drawn it in the other set, right? I got lucky. We picked the right conformation to start with. But you could have drawn it the other way too. And in that case, let's see, this thing over here will be it'll still be pointing up, but now it's equatorial, right? And oh wait, I just butchered that. Okay. In this case, it would still be axial, right? Let's say it's over here and it's equatorial. There we go. Right? And the bromine is pointing down, so now it's also equatorial, and there's a hydrogen up here, right? And the deuterium is pointing down, and this hydrogen is pointing up. Okay. And let me maybe even just erase the rest so that we don't get bothered, right? We draw our ring, we pick, you know, this carbon, and we start going around. We just say one of these is going to be the blue carbon, and we start going around. Right?
At what point does a group like the ethyl group now become too big to be axial? So is ethyl okay?
Yeah, ethyl is going to be fine. Yeah, it's pretty vague, and this is not like a question that I've ever seen a definitive answer to. Tert-butyl is too big. Isopropyl is kind of like how when we were talking about bases, it's sort of small, but like not entirely. Isopropyl would probably be okay to do ring flip. Part of the reason that you can't do tert-butyl, and maybe you'll have to tell me if anybody ever mentioned this to you, so I'm not just dropping this on you out of nowhere. Part of the reason you can't do tert-butyl is because of let me move where it is. So yeah. So part of the reason you can't do this is because these things bump into this tert-butyl. So this is called like 1,3 diaxial interactions. You seen that before? Okay. Yeah, so with tert-butyl, it's too big. If you make this isopropanol, or just an isopropyl group, I mean, it's a hydrogen here too, so it's fairly small, and so you could just rotate it to be in this way, and then it won't bother you that much. It's kind of big though, so I mean, isopropyl isn't necessarily going to be great either, but tert-butyl is really, if there's going to be a problem where the idea is that you can't really ring flip, it's probably going to be tert-butyl, or like some other nonsense like what I wrote down earlier, where it was like a carbon and 3 phenyl groups around it, which is just enormous. So yeah, this ethyl is not going to bother us. And I guess I should also say, besides that, if this even was a tert-butyl, right, and we drew it like this, well, that kind of, I mean, oh, in this case, it was fine. If we drew it in this like axial position, while this, like, you're not going to see this structure but any of the time, you can do this ring flip thing to figure out what it should be normally, because you've already laid it down in chair conformation, so you could just ring flip and it's still going to be right.
In that case, would there be like no reaction just because like the more stable the conformation would not give you antipair planar, or would you do the syn like in a really rare case?
You would have no reaction. Not syn. Yeah, I would not expect them to expect you to write syn E2. like I just in general, you probably shouldn't even mention it, unless for example, like I know with like last workshop, there was a problem that I gave you where it did involve a syn E2 mechanism, and in that case they tell you like that you're doing it, or they'll give some kind of indication that like there is a reaction happening, there is some E2 happening, but well, what's going on? Yet again, and I you guys are probably getting tired of hearing me say it, syn E2 is something to avoid.
If you had like instead of tert butoxide, you had like NaOH, would it still prefer like, because in that case, wouldn't it prefer the Zaitsev product, but would it still go for the H that was anti-periplanar to it? Like regardless of being the Hoffman, even though it's not sterically hindered? I don't know if that makes sense.
The hydrogen would still have to be anti-periplanar because that always has to happen for E2, but it would go after the other hydrogen. So if you had, for example, I'm going to use pink. So if you had OH, it would go after that hydrogen. And so if you gave this OH, well, then the structure that you would wind up getting would look like this, right? And then over here, this would stay exactly the same. Whoops, that's not a bromine, that's a hydrogen.
Okay, because there was like an example very similar to this, and it went after the other hydrogen, and like the explanation given was that the hydrogen was already antiplanar, but I guess like they couldn't do a ring flip or anything in that example.
Yeah, I guess if there's a case where you can't do a ring flip, yeah, then you might have to do that. Yeah. I don't think that they would do it because it's really nasty if they would, but I mean, I wouldn't put it past the people to do something like give you a molecule with the deuterium in it, which kind of says like, oh, look at me, like, you know, you might want to pull off a hydrogen of me, and then have you actually take a hydrogen off somewhere else. That's pretty mean. That's actually really mean, but
okay, thank you.
Maybe they would do something like that. I don't know.
So having a deuterium doesn't make anything any more substituted than having a hydrogen, right?
No.
Right.
Yeah. Yeah. Don't let the presence of the deuterium throw you off. Chemically speaking, it is exactly just a hydrogen. Like it doesn't really do anything else. There's some minor stuff about it kinetically being different, right? It's heavier, so you have to put more work into moving. That's like besides the point though. Chemically speaking, it will act exactly the same. It's just special because it's labeled. So, well, you have to think about it a little bit more carefully in terms of whether you're taking it off or something else. This is the point. Okay. Next. Here we go. It's one of these fused rings, and these things are terrible. Right? Yeah. Let me not use pink anymore. Okay, so we have this O-methyl, right? Which is really small. Okay, it's a really good base. It's pretty small. So we're gonna do E2, and is it gonna be Zaitsev or Hoffman?
Zaitsev.
Yeah, it'll be Zaitsev, right? So okay, this is gonna be. So it'll be the Zaitsev product, and we've got a hydrogen here and a hydrogen here. We're not going to worry too much about, well, where those hydrogens are. So, okay. Make the Zaitsev product. Is this okay? Are we allowed to do that?
If you like drew it in the chair thing, where would the hydrogen that's like where they attach, where the two rings attach, would that be up or down?
Oh, yeah. Yeah, so I actually think this problem's a little bit. Yeah, I was thinking about this, and I like I've looked at the answer before, and they actually have the double bond over here, which I don't know. I think it depends on where this hydrogen is, actually. Because, well, we've kind of, it's one of these really standard problems, which is just to say, like, if you have something like this, where if you have one of these bridge systems, right, like, what does it look like, right? So if you have the hydrogen over here, and this thing is, drawing this is going to be a little bit tough. Yeah, there we go. If it looks like this, then you could do it, right? And this is transdecaline, right? And this is the one that can't do ring flip. Right? There are two ways of seeing that. One is to make this molecule with like a modeling kit and then try to ring flip it, and you'll break your modeling kit. The other way to do it is just to actually like think about it, which is a lot harder. But if we were to try to ring flip it, well, it's hard to draw because it has to move backwards, right? It has to move back here. But this is going to go up, right? And then we have to take just count our carbons now. So 1, 2, 3, and 4. Oops. And 4, right? So here is 1, here's 2. And then we know back here, the carbon has to go down. So here's carbon 4, right? And oh, look at that, carbon 3 has to go way over there, right? And that just doesn't happen.
Would a system like this count like a bridge system?
So I think so, but I've seen before that people call this a fused ring as opposed to a bridged bicyclic system. I'm pretty sure if you're being like really technical, this counts as a bridge system. Yeah.
So then you couldn't get like the double bond at the bridge head because of Brett's thing. Wouldn't that like, because if this is a bridge bicyclic system, then you need like at least 8 carbons, wouldn't you?
Yeah, so you need, with Brett's rule, you need at least 8 carbons in one of the rings, right? And if we treat this, and this is like really like, I don't know, an annoying thing. So we can look at which rings there are, right? So there are, whenever you have a bridge system, there are 3 rings, right? So there's this one, the left one, right? There's the right one, which is over here. And, well, then we've also got this ring. Okay. And this has 10 carbons. So we're okay with Brett's rule. We're all right in this case.
So in this case, you'd get both products then, the one with the double bond at the bridge and the other one.
Yeah. Yeah, if this is transdecaline, then you can do this. If it's cisdecaline, which looks like this, then you get the other product. Because you can't do E2 on that other hydrogen. It's just not an option.
But for trans, we get both, and like there's really no major product, right?
With trans, we would get this one preferably because it's more substituted. Right. And then, well, we're already on the topic of Brett's rule, so why don't I just put up the next problem, which has to do with it. But since we've already talked about it and mentioned, well, we already mentioned Brett's rule. It's not going to come as a surprise that it comes into play here. So here it is. Whoops. All right, I don't know why it's like that. Okay, just all right. No, I got it. Cool. Okay, so again, we're pulling off this hydrogen, right? We're pulling off one of these two, and well, everybody always seems to be really excited to talk about Brett's rule, so I don't think it'll come as at way too much of a surprise that you only get one of the two products, and it looks like this. Okay. So you have to use Brett's rule in this case. Okay. Cool. All right, and let's get the next problem up. It's a synthesis problem, so this is fun. All right. All right, synthesize the molecule on the right from the molecule on the left. All right, we can start this problem in two different ways. And in fact, it might actually work to kind of go in both directions. So there are two things we can do. If you're really good, you could just start from the start and, have a vision and see the whole process all the way through. Usually that doesn't happen though. That's pretty hard to do. So other times you're able to go from the ending product, you're able to see something that's really familiar, something that you know how to do, and you work your way backwards. So that's called retrosynthetic analysis, which is really helpful, and it's super important and powerful. And so we'll use some of that too. Okay. Why don't we start with the front though? Because this is a point that needs to get hammered home, and we might as well start it off right. What can we do with this?
Brominate.
Okay. Can we do anything else?
Light.
So yeah, we could do the BR2 and light. Can we do anything else? Are there any other options?
You could use NBS too.
Oh, yeah. Yeah, you can use NBS also. You could also chlorinate if you want, which in this case would be fine because, I mean, the whole molecule is like symmetric. All the hydrogens are the same, so it doesn't matter, right? But the point is, all that you could do is free radical halogenate it. Nothing else, okay? For all of organic chemistry. Of all the times that I say later in the course you'll learn the exceptions, there are no exceptions. This is it, okay? So, great. We brominate. Okay. And then we've got to do a couple of steps in between, and then we get to the ending product. Well, you might know what to do from here, especially because, well, there's this double bond in the product, and that's a little bit suggestive. But let's say you get to this point and you're like, all right, well, I don't really know what I'm supposed to do from here, right? Like what is the point, the idea? we can instead look at the final structure and we could think, all right, well, how would I have gotten here? Or how do I know how to get here one step backwards? And in my case, what really stands out is this CN group. There's not a lot of ways to make a nitrile. Like, there's not a lot. Yeah, no, there isn't, right? So you're gonna have to get that on there somehow, right? And what is the way that you know how to get a nitrile on?
SN2.
Exactly, SN2. So we want to take the structure that we have right before it, and we want to have some leaving group, and then we'll give it sodium cyanide. Okay, and that'll do SN2. You could write SN2 underneath it if you really want, but you don't have to. That's the nice thing about these synthesis problems. Like, you don't have to write the mechanism. You don't have to explain anything. Just say what you did. It's pretty nice, but anyway.
So if you wrote like SN1 by mistake and it was wrong, that would be like, they would probably take points off. So you should just maybe not write them.
Yeah, you might not want to do that. Yeah, you shouldn't have to. Unless they specify like otherwise and they say like, oh, write what reaction mechanism it goes through. But otherwise you don't have to. Yeah. Okay. Well, we need to go from here and get to there, right? We know we're going to form a double bond. So what can we do on this side, on the left over here?
E2.
Yeah. So let's do E2. Okay. And now how do we put a leaving group on there?
NBS.
Perfect. Yeah. Right. And that puts bromine on there specifically. In particular, puts bromine on there. Okay. And the nice thing is, well, this structure is racemic. You don't have to mention it, but it's worth pointing it out that in this case, everything we did makes a racemic structure.
Could you explain why?
Yeah. So the reason is precisely because nothing that we use has stereochemistry. We didn't give it any stereochemistry. Here we're starting from something that's actually achiral. And we're producing something that's chiral, right? Because this is a chiral center. But it's racemic because what we started with was achiral. We didn't say which chirality it should go to, so it's just going to make it 50-50. It's the only option that it has. It's not going to choose either one of the two stereoisomers. And, well, we know that SN2 inverts the stereochemistry, but that doesn't matter because we didn't have any one particular stereochemistry to begin with. We had a mix of both. So we're going to get a mix of both at the end anyway. Okay. So we've gone through a bunch of these problems. There are more in this worksheet thing. We can keep going through those, but we have a few minutes, like really a few minutes, like 5, which of course, we've spent more time reviewing and talking than doing the problems, but that's okay. You can look at the problems afterwards, right? I hope so. I hope nobody's like, God damn it, every time we don't finish the problems. So, okay, anyway, there are a few minutes left and I'm not super busy tonight. So there are 2 options. So we can go through the remaining 2 problems and, that's nice. Or I also have some extra problems, which are like super hard. And I can give those to you too. I can upload them afterwards too, but it's up to you. We can go through those as well. Okay, wait. Wait. There's a nice feature. Use the participants panel. Say yes if you want to go through the extra problems, or say no if you want to just do the worksheet or go home or something. Although you're also welcome to leave anytime. So yes, yeses. Yeah, some people are using the chat. That's okay too. Somebody's asking if you can be added to the Canvas page. If you want to be added to the Canvas page, send me your pen key, like the first part of your email, and I can add you. Or also, you could also send me an email. You could also send me an email if you're one of these people. You send me an email too, and I can add you right away. It takes me like 2 seconds, so I'll do it. Okay. All right. Yeah. Okay. That's all yeses. Okay. So let's mention a few more problems, and I'll keep going for a little while because I don't have a lot of other stuff going on a Thursday night. Yeah, I feel so bad. My most of my semester has been so busy till now, but now like all of my stuff has ended, which I know is like not the case for most people. So I'm kind of chilling, but that's also kind of good because I can actually help you guys do organic chemistry, which I'm very happy about. So, all right, what do we have? What do we have? Okay, so here is. Why don't I write the problems? You think about them for a moment, and then once I'm done writing them, we'll go through them. So, okay. We'll warm up easy. So what does that make? Okay. Think about it. I'll keep writing. Okay. Hopefully that first one's not too bad, but things are warming up a little bit with the next one. And okay. Oh boy, this one's a behemoth. There's a whole lot more to this structure. And up here, okay. There we go. We get there, and let's see, I could probably fit another one in. Yeah. Okay. There we go. We got 4 problems. I'll upload these to the Canvas, by the way. Yeah. Whenever I give extra problems, everybody is like always like panicking and worrying about whether they can get them or not. I will upload these. Okay. I might still be copying. But well, why don't we get moving? Whenever anybody's ready, anybody want to give any thoughts about this first one?
I'm thinking that because the oxygen has a negative formal charge and it wants a hydrogen, maybe it can act as a base and then the bromine can leave.
Okay, so it's acting as a base and the bromine's leaving. What type of reaction is that?
E2.
Okay, so you're saying E2. And well, I'm not going to zoom in because everybody or people were still copying, but oh, look at that. I can even do partial zooms. Okay. Okay, so you're saying it's E2, cool. And well, it doesn't matter what hydrogen we're going to pull off, right? If we do E2, then well, the structure is going to look like this. Good. Why is it not SN2? You're right. Well, why isn't it?
Secondary?
Yeah, it's a secondary halide. is bad for, it's not good for SN2. This base is also like on the edge of being kind of bulky. It's not very great either. But the fact that it's a secondary halide, that kind of gives us that it's SN2. If it was a primary halide, this might actually be SN2. Yeah, sorry, this is E2. I might have misspoke there for a moment, but yeah. All right, what's up next? This is sodium amide NaNH2 that I wrote here first. Right. So NaNH2. So what's it going to do with this structure over here? What?
Would it take the hydrogen off of the alkyne?
Exactly. Good. Okay. And now what is this thing going to do?
SN2.
So someone said SN2. And does anybody want to contend SN2?
Wouldn't it be SN2 because the phenyl CC, I don't know what that's called, is like a good nucleophile, and that would act as a nucleophile?
So well, I don't think it would be SN2. This is a pretty good nucleophile, and there are times where it can work, but I think we're going to rely again on what we just said previously, which is it's a secondary halide. This thing is a good base, by the way. That's the reason that it could be E2. In fact, that's the reason it does come out to be E2, because this thing is a really good base. If you remember the pKa of one of these hydrogens, it's around 25 or so. So that conjugate base isn't really happy. It's not really very happy. And while this can be a pretty good nucleophile, it's pretty big because it has this phenyl group on it too. So not entirely. This is going to be preferentially E2 because this thing is really basic. From that minus sign, it has a pK. The conjugate acid has a pK of like 25, so it's going to really prefer being that acid. We get the same thing as last time. Isn't that kind of lame? Yeah. All right. Now we got the monster. First, what type of reaction is this?
E2.
It's E2. Which one?
Hoffman.
Yeah, exactly. All right. So, well, okay, we've got this huge molecule and this thing is like terrifying and it took me like 2 minutes straight to write. But why don't I neglect all of that and just zoom in really close on it? And if I go over here, now it's super pixelated and kind of ugly. There's a hydrogen. There's a hydrogen. Nothing there, it's empty. Okay, there are literally 2 hydrogens we can pull off of this. That is it. That is all of amidst this whole molecule. That is the only reaction that we can do. Like, go ahead.
Well, it'd be the one on the methyl because it's a bulky base.
Yeah.
Like exactly. That's the hydrogen that leaves.
Exactly. So all of that extra stuff is just a huge red herring. It's irrelevant. You just get this, and there's all the other junk on the carbon ring. I'm going to skip drawing it because it doesn't do anything. Not relevant. Go ahead.
Can you please repeat why it removes the hydrogen that's on the methyl?
So it was the so we picked the hydrogen on the methyl because it leads to the less substituted product. In other words, it's the one that's like easier to get to, you might say. But we have a really bulky base, so it's Hoffman. was
And-
using a. Go ahead.
And so it's gonna form a Hoffman product. That's how you know, like, you want to remove the hydrogen that makes it less substituted, because Hoffman products are typically less substituted.
Exactly. Yes. Yeah. If we were to pull off the other hydrogen, noticing, in fact, there's only one other hydrogen in the first place, right? So there's not a lot else we could do. If we were to pull off the other hydrogen, we would get this, which is more substituted. So that's bad.
Wait, so for E2, isn't it like, is it not a rule that typically you can only ever remove the hydrogen that's like directly next to the leaving group, or not really?
Yeah,
Like, I
so
didn't know-
that's true. Yeah.
Sorry, I was just saying, so then how is it even a possibility for you to remove that other hydrogen?
So, I mean, if we zoom in to what's going on in this ring and kind of skip all the rest of the stuff, so here we just have this bromine and the hydrogen separated by 2 carbons, which is good for E2. And then we also have these two separated by 2 carbons. Another way that I could draw this, which might be a little bit more intuitive, is if I were to draw it like this, and then there's a methyl over here, and I could even draw it anti-periplanar, right? And then there's this ring, and there, there's all this extra ring stuff, but I'm not really worried about that. Kind of care about is just the fact that there's this, right? And yeah, there's all this extra ring stuff too, but it doesn't make much difference, right? It's just that I could choose either of these two. So I could use either of these. Oops. Go there and then take this off. Or let me use orange. Got to pick more interesting colors. It's kind of hard to see, but it's okay. Or you could do that. Either of these two are okay.
Okay, so it's like, so long as it's like the distance between the leaving group and that hydrogen is just like maximum 2 carbons away. Is that the idea?
Yeah, so if they're on the same carbon, you can't actually do E2. So for example, if you have like a, I don't know, let's say you have something like this structure, you actually can't do E2 on this. Oops. So you can't do E2 because, well, what's going to happen, right? Let's say you have this OH minus, right? And you want to take off this hydrogen. These electrons have to go somewhere, but they're just going to stay on that carbon. They don't have anywhere else to go, right? And, well, then what? Right? From there, we've got this, and then, well, doesn't, like, we can't go anywhere from there. We can't make a double bond with anything. In particular, if we try to move these electrons over here or over here, we'd get carbons with 5 bonds on them. And that is never okay. Never. And it's actually, it's something to always look out for because, well, it's something that can happen kind of commonly, to say, like, to be doing like all this math and going through it, and then you're like, oh yeah, just move a double bond here, or taking hydrogens off of the carbon with the leaving group on it, is like a really common thing to do when you're getting into like all these like big complicated structures. So it's always, like, forever and always a good thing to be looking out for.
Got it. Thank you.
Okay. Yeah. Okay. I'll erase this stuff. because it takes up, well, just to keep the solutions consistent. Okay. All right, cool. Over here we have, well, you already said it, so I'm not going to go into it, or I'm not going to ask you again, but we have E2 and we have Hofmann elimination because this is a really bulky base, right? We could tell that just by looking at the base itself that this is E2 and it's going to be Hofmann, right? And so, well, there's a hydrogen and there's a hydrogen. And those are the only ones that are next to the chlorine. So maybe this final product isn't that interesting because we take off one of these, right? We take this off, it goes onto here, this chlorine pops off, and that's it. Not the coolest thing. Okay. All right, that one was a little bit uninteresting. Let's get into the serious stuff, because these were a little bit easy. Okay, here we go. I picked some real nasty ones too. So, okay, provide a mechanism for this reaction. So if we're given this structure, and over here it's got these two methyls, here it's got a bromine, it's connected, right? And here it's also got a methyl. You already know it's going to get bad when you see something like this, right? So let's say you're taking this and you're putting it in, oh, I don't know. Let's give it acetic acid and heat. Okay, and what it comes out to be is way uglier, and it looks like this. Okay, that's one problem, and I'm even going to leave myself a whole ton of room because it's going to get ugly. And why don't I write the next one also? Well, that's a question mark, right? And the question is, so if we're given something like this, well, what I'm going to tell you is that the final product is racemic. Oops. All right. Now these get a little bit worse and tough and challenging. This top one, they might not ask something that's this complicated, but well, it's always good practice to look at some of the hard stuff, right? So let's do that. Oh, whoops, I wrote this on the wrong paint layer. That's okay, whatever. Let's do that. All right, whatever. Here we go. Let's try to figure out the mechanism. And with this one, well, there's a few things that we can fall back on, which will help us here. Okay, so we know that we're heating this thing, this big thing. Okay, and in fact, if we say that this is the solvent, or even if it's not, and we say like, oh, this thing is in water, I don't know, whatever, we can say it's in water if we want, sure. What maybe what it doesn't matter, right? This is a polar protic solvent. So what can we do with this to start us off?
If it's protic, we'll do SN1 at some point. But
Okay. Well, we're giving the mechanism, so we have to do it step by step. So what is like the first step if we wanted to do SN1?
to form a carbocation.
Exactly. Right. So, well, this is a mechanism, so we have to write out each step, right? We have to move electrons and everything too. So let's move our electrons, form the carbocation. Step 1.
So can like the bromine just pop off spontaneously? Or
Yep.
does like, or it's the solvent that helps that happen?
The solvent doesn't make it or help it happen. But the thing is that, like, since you get a carbocation out at this end, you need to have the right solvent for this to even like exist, to happen. Because otherwise, like, you're just never gonna make this. There we go. Okay. I don't know why it wasn't letting me erase. Okay. Now what?
Would there be a rearrangement?
Oh, yeah. Yes, there will be. There will be a rearrangement. What's going to rearrange?
Would the carbocation go to the bridgehead? Because it would be like tertiary.
Okay, so are you saying to move this over here?
I feel like that would be really unstable because the bridgehead is like already pretty straightened. So like.
Oh, that's true too. Yeah. Yeah. I mean, I was going to say that if you were to do this, right, what you would wind up getting would look like this, right? Which doesn't get you to the final structure. But hey, the bridgehead will be strained too. So that's extra reason not to do it. Well, fortunately, they're not asking you to justify why the wrong things don't happen. They're just asking you to say why the right thing does. So fortunately, we don't have to explain that the bridgehead causes that not to happen. But anyway, okay, what else can we move? Let's say we move one of these methyls, right? And I'm using a forward arrow again, remember. Let's say we move one of these. That's also pretty nice. That's also a tertiary carbocation, right? That's good. That's stable. It's very nice. Doesn't get us to our product though. So nice try. That's not going to do it either. Anything else that we can move for a rearrangement? So I'll just remind us, we've already done this. We can't do it. Already done this. Can't do it. Anything else?
Could you move the bridgehead? Like just the bridge? I don't know if that's what it's called, like where it like meets the ring.
Ah. Now that's interesting. Yeah. So let's take this whole thing and now we're going to move it over here. Okay. And so this is a complicated thing going on. So I'm going to keep everything exactly as is, with the exception of this bridgehead that I just moved. Now over here, this is the same.
So did you just move the foot by the methyl, or you moved like the top of the bridgehead down?
so I took the top of the bridgehead and I like shifted it over. So I broke, in other words, I broke this bond and I formed this bond. Okay. And I hate to say it again, this doesn't get us the final structure. Because look, at this final structure, we have this guy up here, right? With the 2 methyls, which is correct, right? It's just standing up there on its own. But on one side, we have 1 carbon, and on the other side, we have 3 carbons. But our final structure has 2 and 2. That's still not it. I promise there's a real answer. There's one. There's one thing that we haven't moved. Okay. Actually, I think there might be more than one thing, but oh, whoops. But no. Okay. I'm not, well, at the cost of sitting here for a long time, I'll tell you what we do. So what actually happens is we need to take this side of the ring and move it. Okay. Bear with me. This is where it gets kind of whack. So let's keep everything as we drew it again, because this is complicated and well, okay, see, I already failed to draw it. Oh my God, this is the worst. Why did I give this problem? Okay, so this is what we have, right? And then back here, there's that part of the ring. There's a bond there. And we just moved it to be over here. And so now, this guy up front has the positive charge. It's a tertiary carbocation. That's what we wanted, right? And this looks like it can work. Why don't I redraw this? Oh, look, I'm going to do the really fancy thing. Look at this. Oh, yeah. One of my professors started doing this in class, and I was like, what a lord. And then I was like, oh, man, I can do this too. Why don't I... Now I can't draw anything. Oh, my God. Kill me. All right. Please. Please let me draw. We were so close. Let me. Bear with me. I'm gonna close this and reopen it because, well, I'm not. As I've said, I'm not good enough with Photoshop to really do it. I'm gonna reopen it. We were so close. We were almost there. We really had it. So anyway, the point is that you have to move like one whole half of the ring to do this. Okay. Oh my God. I'm in the wrong folder. I have a folder for Organic Chem Lab too, because I'm also taking that alongside you guys, by the way, in case that gives you faith in the person who's teaching you organic chemistry. Yeah. Because I was planning to take it like senior year, and then they changed it, and they made this stuff where everybody has to take it anyway, whatever. Okay, I got it back up. Here we go. Okay. Got it. Can I draw? No, I literally can't. This is, oh my God. This is gonna kill me. Okay, I can kind of draw now. All right, whatever. I'll take what I can get. I'm so sorry. Here, let me select this whole area so I can draw within this area, right? So this is what we got. All right, and I can redraw this. Let me use a slightly smaller brush. So I can redraw this, and I'm kind of thankful that I drew this in a slightly coherent way, because otherwise, like, I wouldn't be able to figure this out at all, right? But I can redraw it to look like this. I didn't do anything. I didn't move any electrons. It didn't move anything right there. I just redrew it. In other words, I took this thing here, and I kind of, like, if you imagine, I like rotated it this way. I like kind of flipped it on its side so that it was laying flat. Okay. I think you got the rest. From here, just stick on this acetate. Okay. You got it. This one, that you can take it from there. Okay. What a really nasty problem. I saw this one and I was like, oh, they're gonna hate this. And then, well, you've seen it. This is probably a harder mechanism problem than you should expect to get. But it's all about rearrangements. You have a carbocation, right? That's the whole point. Okay. Let's see if I can actually write. No, I still can't. All right, I still got to do my jank broken solution. Oh my God, I can. Oh yes. Okay. All right. Good. It's magically been resolved. Whatever. All right. So here's what's next. We've got this structure over here. We have this acetate anion. Okay. Cool. Right. And there's this O-tosyl, which is an excellent leaving group. It's like a super nice leaving group, in fact. Right. It's such a nice leaving group that you can forget about the fact that this thing sucks, and you can get rid of it. Okay. So what type of mechanism is this going to be? What reaction is it here?
Is it SN2?
Yeah. So this is just going to be SN2. We'll just say it's SN2. The point is, this is the less interesting part of the problem, but whatever, right? Okay, we can get SN2, and okay, we get this out at the end. Great. Okay. Yeah. So this will be SN2. The question is, when we do it over here, when we flip where this O-tosyl is, then it's not just SN2. We get this whole racemic mixture. Okay. In fact, we get both stereoisomers. So we not only do we change the stereochemistry here, we also change it at the bottom. So we actually we change both stereochemistries. Okay. And the question is how? There's no way to do this without giving the mechanism. So.
Is it somehow like both SN1 and SN2 or something? I feel like that doesn't sound very likely.
Yeah, but like, how would that work, right? Yeah, up at the top, well, we have this O-tosyl, and if we could have replaced it, we just would, and then, well, nothing interesting would happen. So what can we do instead? All right. Well, why don't we do what we always do? draw a ring. Okay. And okay, yeah, we'll do that. Okay. And this is already in a pretty nice conformation, so I'm going to keep it that way. But what I'll do, and just this is just to make things a little bit more suggestive for all of you, so that you kind of see what's going on. You could have something like this. Okay. Now what can I do?
Wait, are you allowed to just move it from axial to equatorial?
Oh, oops, I just drew it kind of poorly. It's still supposed to be yeah, I meant to just, there we go. I'll draw it that way. Well, what can I do with that?
Can you connect them with like the H and the O?
Yeah. You actually can't really touch the hydrogen so much, just because you don't want to break a carbon hydrogen bond. But look at this. Oh yeah, that tosyl is just waiting to get taken off, right? So look, we've got this oxygen and it's got electrons. It's a pretty garbage nucleophile, but it's right there, right? And this is a great leaving group, so it's kind of also right there. This is going to come up and take this off. Okay. So this here is SN2. Right? And now yeah, we get a plus charge over here, but whatever, right? And now we get a ring that looks like this. Okay. This thing has a plus charge over here. It's a really good leaving group. So what can we do, given that there's a bunch of acetate floating around? What do we do now?
Maybe you can like move the double bond electrons up to the oxygen to complete its octet, and then as a result of that, you want to take like the electrons from the ring connecting place for the other oxygen, so it can kind of just like break off.
Ah, okay. So it turns out you actually don't need to. Well, also, so if you move these electrons up to the oxygen, for example, this thing, yeah, let me draw the whole ring just so it's not just floating in space. So if you do this, you wind up forming a carbocation over here.
Oh.
That doesn't really hold up. This oxygen actually already has its octet full, so we're kind of okay with what we have. It's kind of like ugly and messy, but it works. And what we might want to do is just treat this whole plus charge with the oxygen, this whole extra thing that we just kind of stuck on there. We might want to treat that as a leaving group, so we can take it off pretty easily, right? Because as a plus charge, it'll make a pretty nice leaving group. So how do we actually use it as a leaving group? What do we do?
Could we do SN2 again?
Exactly. Except now we take the outsider and do SN2. Okay. So now through SN2, well, I guess I'll draw the whole ring out again. We can do this. There's a hydrogen down here. Okay. So this that we just got out at the end, is this structure. Okay. That is this. That's one of the two. And then how do we get the other? Well, actually, I didn't remember where this was going, but we can get the other because, well, we can do resonance here. And so when it's in this position, now we could do SN2 over here. All right, and this looks like this. So this hydrogen flips down, and then this guy points up. Okay. And if you want to convert that, here we go. So we got both. And look at this. Look, they're even racemic. Right? Well, they're proper enantiomers, right? They're complete mirror images of each other. So we got them.
Couldn't you say they're the same thing?
They're not, as it turns out. There's no way to rotate this guy down here so that it becomes this. Well, that's why I don't draw with my mouse, by the way. A total mess. Yeah, you can't. So if you can imagine, for example, flipping this like 180 degrees this way, you're gonna get the same exact thing. And yeah. It's one of these things where it's always like, you really think that it looks like you should just be able to flip one and get the other, but they're not. They're really different compounds.
Yeah, I see now. Yeah.
It's a real pain in the ass, but yeah. Yeah, that's the case. Cool. That goes through the problems that I had, at least I think the interesting ones. These are the good ones. Yeah, I'll put this stuff up. Of course, I think that kind of goes through the stuff that I had to talk about anyway, and there's an extra 40 minutes, so it was a good time to have anyway. Yeah, if you haven't filled out that sign-in sheet, please do. I'll send the link again. Please send it out. Please do. Please do. It's good. It's good for me. It's good for you too. It doesn't really get you anything, but it's good for you anyway. Yeah, that's it. I mean, good luck on the quiz, I guess I should say, first off. Who knows? Maybe they'll make it. Maybe they'll be a little bit nicer given the amount of serious backlash that there was last time. Oh, I shouldn't be recording. It's okay.